Hi everyone, we are going to finish up this basically first introduction to structure by talking now about how do we characterize non-crystalline materials, specifically semi-crystalline and amorphous materials. So these materials basically, or these types of structures basically correlate to quite a few different materials, so polymers, liquids, glasses, and many more. Previously, we've talked about this long-range order, long-range translational order, long-range orientational order, and we've talked about how we could propagate a lattice in 2D or 3D into infinity. However, there are materials that basically a metal will have short-range order and long-range order. Polymers, other amorphous materials or semi-crystalline materials will have short-range order and then some amount of long-range order, but not to the degree where we have a lattice and we could propagate it out into infinity. Now, this makes it quite difficult to, how do we characterize or how do we actually kind of quantify the amount of long-range order in our material? Luckily, we actually have a method to do that. And actually, if you look at some of my MECH293 videos, you can see actually how you can actually calculate this in Mathematica. So you could actually calculate what's called a pair distribution function or a radial distribution function or pair correlation function as well. So what the PDF effectively does is, you can actually see it here. I am going to pick an atom as my origin, and I'm going to start to draw rings. And the instant this ring starts to hit other atoms, I am going to start counting. So I'm going to count the number of atoms that ring hits, and I'm going to divide it by the average density in my system and the volume of that. Basically, the number of atoms divided by the volume and basically the density in the system. So it's basically, when I see a spike, it means I've hit this ring of atoms, and I'm going to keep drawing, and then the same thing's going to happen. So you see a dip because there's empty space, and then here. So I have my next ring. So this would be, second hump would be my second nearest neighbor's distance. This hump here, this position would be my first nearest neighbor distance. This would be my second nearest neighbor distance. And eventually, as you keep drawing, you're going to kind of baseline here. Now, I'm not going to just do this for one atom. I'm going to do it for every atom in my system. So this is kind of an averaged quantity. And that kind of tells you the power, is that when I see the spikes here, it means that for every atom, there's this basically perpetual, or this characteristic distance in my material. Now, if I have a liquid that's just splashing along, or just atoms that are kind of moving around a lot, or a gas, I'm not going to see any kind of characteristic distance except for that first distance where, carbon is next to carbon, or et cetera, et cetera. If I have a material like a polymer that has short-range order and some long-range order, I'll see a curve that looks something like this. Here, this is a metal. I'm going to see these spikes and then nothing. Spike, nothing, and it's going to continue to infinity. Why is that? Well, we know in our 2D lattice that if I were to do the same exercise of PDF and RDF, so for example, let me do one more line. So if I pick this atom, I know I'm going to hit this first nearest neighbor distance, then I'm going to hit these guys. Where am I at? And then I'm going to hit the next nearest neighbor. So it's basically, I'm going to hit nothing, nothing, nothing. Boom, I've got them. Nothing, nothing, nothing. Oh, boom, I got these guys. Nothing, nothing, and then et cetera, et cetera, et cetera. So as it goes. So that's kind of the key idea here. And for a polymer, I could have a graph that looks like 1, 2, and then nothing. Or I could have a polymer that looks like spike, spike, spike. So this material would have much more long-range orientational and translational order. This would have less long-range order effectively. Now, a material is not going to have more short-range order, but basically it lacks long-range order. One of the cool things, and you could kind of read through this in the notes, is that we can actually, if you integrate the peak and multiply out by the average density, you could actually calculate the number of nearest neighbors here. So you can actually calculate that out and integrate this to get the number of nearest neighbors. And again, here's your first nearest neighbor distance, second nearest neighbor distance, if you have a metal. So this was lecture 1. This is the atomic structure of materials. And next time we're going to get into the fascinating world of defects. And then we're going to get straight into intense solid mechanics math. So looking forward to seeing you then. Thanks.